Hello. Today we're going to be talking about rational functions and how to graph them. So, first of all, what makes it rational is if you have an x in the denominator. If you have an x in the denominator, that's what makes it rational. And so graphing these is not really going to be too much different than graphing any other function. So if I have, say, an f of -1, what I used to do before was the exact same thing I'm going to continue to do. I'm going to put a -1 in the spot of each x. So I'm going to have a -1 minus 3 on top, a -1 minus 2 on the bottom. I'm going to follow my order operations and subtract the top. -1 minus 3 is a -4 over -3. A negative divided by a negative is a positive. So this is just going to equal 4/3, or you could even call this 1 1/3. The thing about rational functions is there's one issue you really have to watch out for. And I'm just going to pick f of 2 to show this point. If I put 2 in each x, I want you to notice what happens. I have 2 minus 3 and a 2 minus 2. So as I solve this, 2 minus 3 becomes a -1 over 2 minus 2 is a 0. But here's the problem. You can never divide by 0. If you divide by 0, this is undefined. So if that's undefined, you can't put it on a grid. You can't put it on a graph. So this is going to create an asymptote or a hole. It's going to end up being a point of discontinuity. Okay, so how do I graph these? Well, what we're going to do is we're going to take and we're going to make a table. So as I make a table and I plug these values in, if I plug a -1, I will get 4/3 or 1 1/3. If I end up putting a 0, some people get confused, well, you can't divide by 0. When I put a 0 in each x spot, you're not actually going to have a 0 on the bottom. So I'll get a -3 on top over a -2, which makes a positive 3/2 or 1 1/2. So I get a 1 1/2 when I get x is 0. When I plug in a 1, 1 minus 3 equals a -2. 1 minus 2 is a -1. Equals just a 2 over 1, which is just equals to 2. Okay, well, that works out nice. And of course, as I plug in a 2, I get this undefined. So in my table, I'm going to put kind of a scratch, kind of a line across it, saying that when x is 2, y is undefined. There is no value. It's a point of discontinuity. Then I can plug in my 3 and just keep on moving. Now, 3 minus 3 is a 0 over 3 minus 2 is a 1. 0 divided by anything still equals 0. That is a point over 3 up and down 0. And we just keep on rolling with this. So plug in a 4 minus 3 equals 1. Over 4 minus 2 is 2. So that looks like a 1/2. And 5 minus 3 equals a 2 over 3, so that's 2/3. So using that equation, using that formula to solve for all these y points is still how we're going to end up graphing these. So when I do graph these, and I take all these points and plot them, what this is going to look like is if I go -1, I'm going to go up 1 1/3. I'm going to have to kind of estimate it. 0 is up 1 1/2, a little bit more. Over 1 up 2, and I don't know if you can tell, but it's just starting to curve just this little bit. At 2, it is a dash, and so that's going to be an asymptote. And so 3, 0, 4, 1/2, 5, 2/3. Now, as you look at these 6 points, can you tell that they're curving and they're going to get closer and closer and closer to this 1 value? And so there's going to be a horizontal asymptote also. But what happens as you get closer to this vertical asymptote, this green line? What's going to happen is it's going to get closer and closer and closer to that asymptote. And this is what the graph is going to end up looking like. Now, if you want to pick a few more of those points, if you want to pick 1.5 to see it going up, or 1 3/4, 1.9, you're going to notice it's going to get higher and higher and higher. So this is what graphs look like. So the big thing you need to know is that with rational functions, you're going to have breaks in continuity. That means unlike polynomial functions, which can be traced with a pencil, never leaving the paper, not all rational functions are going to be traceable. Breaks in continuity appear as a vertical asymptote. That was our dotted line. But they could also be a point of discontinuity. So as you recall that an asymptote is a line that the graph of the function approaches but never crosses. A point of discontinuity is just a hole in the graph. So there are 2 types of rational functions. The first one has a vertical asymptote, and that looks just like this one right here. You can see the vertical asymptote. How do you know where that asymptote is? Well, it's really about what makes this denominator equal 0. If I plug in a 3 in the x spot and I go 3 minus 3, will that end up making it equal 0? Because it's this dividing by 0 that creates our asymptote. So whatever makes your denominator a 0, that's where your vertical asymptote or hole is going to be. Okay, so what's the other method? The other one is called a point of discontinuity. And if I just happen to have a rational expression where I have 2 values that will cancel each other out, then what this will end up equaling is an f of x or y equals x minus 1, whatever was left. So then, as you look at this as a y equals x minus 1, that's a linear equation. And so you have a slope, you have a y-intercept. So slope in here, when it's not there, I assume is 1. And my y-intercept is -1. So I can see that there's going to be a point here at -1 on my y-intercept, and rise 1, run 1, rise 1, run 1. Well, they asked you to graph this equation, not this equation. Now, if they just asked you to graph y equals 1x minus 1, it's just going to be a continuous line. But if they ask you to graph f of x equals x plus 2 times x minus 1 over x plus 2, that means there's a denominator here that could be at some point equal to a 0, which creates a point of discontinuity. So whatever makes this bottom equal a 0, in this case, can you see it? If I plug in a -2 plus 2, it ends up making your denominator 0. Well, then you're dividing by 0, and you're getting undefined. So this -2 is going to be the spot of your point of discontinuity. It's going to be the spot. So notice this was an x was -2. That means in the x, I'm going backwards 2. So somewhere on this x equals -2 line does not exist in our graph. But because it canceled out, instead of being an asymptote, it's going to be just a hole. So you might want to look at that again. If it cancels, it's going to be a hole. If it does not cancel, it's going to be a vertical asymptote. Now, they might not look like that. In this case, you have an x squared minus 25 over x plus 5. But remember that this thing equals an x plus 5 times an x minus 5. So you might not notice it right away, but if I have an x plus 5 and an x plus 5 on top, and it's all being multiplied, so it's all factored, yes, you can cancel these, and then this will end up equaling y equals x minus 5 is the only thing left. So if you want to graph y equals x minus 5, that's the shortcut. Yes, that will save you a lot of time. But remember that they asked you to graph this full equation, which means this x. What would make that denominator 0? A negative 5? When you have a negative 5 on your table, it will make it undefined. Which means if I go back 1, 2, 3, 4, 5, somewhere on that vertical line you are going to have a hole. How do you know where? You'll have to graph the rest of the line. The shortcut is use this as your slope-intercept. So minus 1, 2, 3, 4, 5. Your slope is rise 1, run 1, rise 1, run 1, or down 1 backwards, downward, backwards. And so as I follow this down, you can tell that right here is where the point should be, but because of that point, that is going to be a vertical asymptote. So everything else is connected, everything else is solid, but at that one point, it's going to be a hole. Hope this helps. Have a great day.